The closest star to Earth sits 25 trillion miles away. A rocket moving faster than anything we have ever built would take 70,000 years to reach it, and that is our nearest neighbor. If aliens exist out there, crossing that gap to find us means defeating fuel limits, radiation, time, and physics itself. We will walk through the actual engineering, the real proposals, the exact points where the math breaks. If you are enjoying the mission, subscribe and leave a like. It helps the crew. Stand at the launch pad. Picture the fastest object humans have ever built. That is the Parker Solar Probe, a spacecraft about the size of a small car, and it moves at roughly 400,000 miles per hour at its peak. Engines off, gravity doing the work. 400,000 miles per hour. That is fast enough to circle Earth in under 4 minutes. Now pointed at Proxima Centauri, the nearest star to our solar system. 4.2 light years away, 25 trillion miles per hour. Your arrival time is roughly 6,800 years from now. 6,800 years ago, humans were just learning to write. Egypt had not built a single pyramid. The wheel was a new idea, and the Parker Solar Probe, humanity's fastest achievement, would still be less than halfway there. That is the opening problem of interstellar travel. Before fuel, before radiation, before every engineering nightmare waiting further down this mission briefing, there is the raw, unforgiving size of the gap. And Proxima Centauri is close. It is the nearest star we have. The galaxy holds somewhere around 400 billion stars, most of them separated by distances that make this one look like a short commute. Here is a way to feel the scale instead of just hearing it. If you shrank the solar system down so that the distance from Earth to our star was 1 inch, then Proxima Centauri would sit about 4.5 miles away, 4.5 miles to the nearest neighbor, on a map where our entire home system fits in. 1 inch. The next nearest star cluster beyond that would be roughly 9 miles further, and the center of the Milky Way would be around 2,000 miles away on that same map. Space does not separate star systems with emptiness. It separates them with distances that swallow time itself. Now consider what this means for a visiting civilization. If an alien species wanted to send a crewed ship to Earth, they would need to sustain life, power, navigation, and structural integrity across a journey measured in thousands of years at speeds far beyond anything we can currently engineer. And they would have to decide to make that journey before knowing for certain that Earth holds anything worth finding. The light reaching their telescopes, showing life on our planet left here hundreds or thousands of years ago. They are always chasing old signals. This is confirmed physics, confirmed distance, confirmed travel time. Every number in this chapter comes from measurements backed by over a century of astronomy, and Proxima Centauri is the easy case. It is our closest neighbor. Everything else in the galaxy sits farther away. There is a second layer to this problem that most people skip past. Even if a civilization solved the speed problem, even if they built something that traveled at 1% the speed of light, a journey to our star system would still take 420 years each way. That is not a mission. That is a dynasty. Every crew member who climbs aboard would die long before arrival. Their children might too. The ship becomes a world unto itself, isolated, self-sustaining, carrying a population across a void with no guarantee of what waits at the other end. 6,800 years at our fastest speed, 420 years at 1% light speed. Both numbers describe the same brutal truth. Distance alone, before anything else, makes this extraordinarily hard. But distance is actually the simplest problem on this list. Because once you accept that you need to travel fast enough to make the journey survivable, you immediately walk into the next wall. A wall that has broken every interstellar proposal ever put to paper. The fuel math is waiting, and it is worse than the distance. A highway sign tells you what the law allows. You could break it, you might get away with it. The sign is a rule set by people, and people can change rules. The speed of light is different. It is a structural feature of the universe, the same way the number of dimensions is a structural feature. You cannot negotiate with it. You cannot find a loophole in it. And the closer you push toward it, the harder the universe pushes back, in ways that have been confirmed in every particle accelerator ever built. Light travels at roughly 670 million miles per hour in a vacuum. Every photon, every ray of light hitting your face right now, moves at exactly that speed. And here is the part that took physicists years to fully accept. Nothing with mass can reach that speed, ever. The reason is built into how mass and energy relate to each other, which Albert Einstein described in 1905. As an object with mass accelerates, it requires more and more energy to keep accelerating. The faster it moves, the more energy each additional mile per hour costs. By the time you approach the speed of light, the energy required to accelerate even one more mile per hour becomes effectively infinite. The universe runs out of available energy before you get there. Scientists have confirmed this directly. Particle accelerators like the Large Hadron Collider in Switzerland push subatomic particles to 99.999% the speed of light. Getting those final fractions of a percent requires staggering amounts of energy. The particles never cross the line. They approach it asymptotically, always getting closer, always falling short. For a spacecraft, this means you are permanently locked below light speed. Your maximum theoretical ceiling, given unlimited energy, is something just under 670 million miles per hour. And at that speed, a trip to Proxima Centauri still takes just over 4 years. Every star beyond that takes longer. Here is where the engineering picture shifts. Traveling at even 10% the speed of light, 67 million miles per hour, would be a civilization-defining achievement. Every rocket we have ever launched maxes out well below 0.1% of light speed. The gap between where we are and where we would need to be is enormous. But there is something else hiding inside the speed of light that most mission briefings gloss over. When you push a spacecraft to a meaningful fraction of light speed, the physics of time itself changes for everyone on board. This is called time dilation, and it is confirmed by experiment. Atomic clocks flown on aircraft run measurably slower than identical clocks left on the ground. The effect at aircraft speeds is tiny, fractions of a microsecond. But at 30, 50, or 90% of light speed, the effect becomes dramatic. A crew traveling at 90% of light speed would age roughly half as fast as people back on their home planet. A 10-year journey for the crew could correspond to over 20 years passing at home. At 99% light speed, the gap grows further. The universe outside the ship ages faster than the ship itself. For an alien civilization, this creates a strange and sobering calculation. Send a crew on a multi-decade voyage, and the civilization that launched them may look completely different by the time the crew reports back, if they report back at all. So the speed of light seals the travel time in place. Physics does not offer a shortcut. Every proposal that claims otherwise, wormholes, warp drives, faster than light jumps, lives in theoretical territory with zero experimental confirmation. The universe has one rule about speed. Everything obeys it, and obeying it means you still need fuel. Enormous, crushing, impossible amounts of fuel. The equation that governs how much is the next thing standing between any civilization and the stars. Konstantin Tsiolkovsky was a Russian schoolteacher in the late 1800s who spent his nights doing rocket math before rockets existed. He derived an equation describing exactly how much fuel a rocket needs to reach a given speed. Simple to write, devastating to apply. The equation says this: to accelerate a spacecraft, you burn fuel and throw it out the back. The thrust pushes you forward. But the fuel itself has mass, and that mass requires more fuel to accelerate it, which has more mass, which requires more fuel. The relationship between the speed you want and the fuel you need is exponential, meaning it grows incredibly fast. For a rocket going to orbit, this is already brutal. About 80% of a typical rocket sitting on a launch pad is fuel. The payload, the actual useful cargo, is a small fraction of the total mass. Now apply this to interstellar travel. To reach Proxima Centauri in a reasonable human lifetime, say 100 years, you need to travel at roughly 4% of light speed. That is around 26 million miles per hour. Using the best chemical rockets we have today, the fuel required to reach that speed would be so enormous that the ratio of fuel to spacecraft becomes essentially impossible. You would need a fuel mass many millions of times greater than the mass of the ship itself. Engineers have known this for decades. The Tsiolkovsky equation does not care about your goals or your budget. It answers with math. So researchers began looking at more powerful propulsion systems. The most promising confirmed candidate is a nuclear pulse drive. Project Orion, developed seriously by the United States government in the 1950s and 60s, proposed detonating small nuclear bombs behind a large blast plate at the back of the spacecraft. Each explosion pushes the ship forward. The energy yield per unit of mass is vastly better than chemical rockets. With nuclear pulse propulsion, a team calculated you could theoretically reach around 10% of light speed. A trip to Proxima Centauri would take about 40 years. Still a lifetime. Still a one-way journey for the original crew. But physically plausible on paper. The catch is what you carry. Even at 10% light speed, you are accelerating to that speed, and then, critically, you have to decelerate when you arrive. Deceleration costs as much fuel as acceleration, so your fuel load doubles. Now your ratio of fuel mass to ship mass grows again, exponentially. Tsiolkovsky does not forgive the return leg. A team of engineers in the 1970s, under a study called Project Daedalus, worked out a detailed design for a robotic interstellar probe using nuclear pulse propulsion. They calculated it would require roughly 50,000 tons of nuclear fuel to send a probe to Barnard's star, about 6 light-years away. 50,000 tons, no deceleration included. The probe would fly through the destination system and keep going, just flying past. No stopping. And still 50,000 tons of fuel. Now scale that up for a crewed ship that needs to stop, carry life support, food, water, shielding, return fuel, and enough genetic diversity to sustain a population. The fuel numbers become a number that no civilization could physically gather from a single solar system. And this is still assuming conventional physics. No exotic shortcuts. Every engineer who has seriously studied interstellar propulsion eventually arrives at the same conclusion. The rocket equation does not bend. It forces a search for something fundamentally different, a physics outside what we currently use. That search has produced some genuinely creative ideas, and one of them brings us to the most energy-dense substance ever confirmed to exist. Something that makes nuclear fuel look weak. Something so powerful that producing even 1 gram of it would require more energy than all of humanity currently generates in an entire year. Antimatter sounds like something from a screenplay. It is real. Physicists produce it routinely in particle accelerators. When a particle of antimatter meets its corresponding particle of regular matter, both are completely annihilated and converted entirely into energy. Every gram, fully converted. Zero waste. Compare that to nuclear fission, where only a fraction of a percent of the fuel mass converts to energy. Antimatter annihilation is the most efficient energy release physically possible. 1 gram of antimatter annihilating with 1 gram of regular matter releases energy equivalent to roughly the bomb dropped on Hiroshima, confirmed by particle physics. For interstellar propulsion, this matters enormously. A rocket using antimatter annihilation as its energy source would need far less fuel mass than any nuclear design. Theoretical calculations suggest a spacecraft could reach a substantial fraction of light speed with a fuel load that is at least manageable compared to the insane ratios demanded by conventional rockets. The problem is production. The entire history of human particle physics research has produced roughly 10 billionths of a gram of antimatter, total, across all accelerators, all countries, all decades of work combined. At that production rate, gathering enough antimatter to fuel even a small interstellar probe would take somewhere around 1 billion years. 1 billion years is longer than complex animal life has existed on Earth. The energy cost is the core issue. Making antimatter requires shooting high-energy particles at targets and capturing the antimatter byproducts. The process is extraordinarily inefficient. For every unit of antimatter produced, the energy input is roughly 10 billion times greater than the energy stored in the antimatter itself. You spend 10 billion times more than you get. A team at Penn State worked out detailed numbers for an antimatter-powered mission. Even with optimistic assumptions about production improvements, fueling a crewed ship for a trip to the nearest star would require an energy infrastructure orders of magnitude beyond anything Earth currently produces. you would need to capture a significant fraction of our star's total energy output for years just to produce the fuel. That is a Kardashev Type 2 level of energy use, a civilization that has harnessed its entire star. We are nowhere near that. For context, humanity currently uses roughly 10 trillion watts of power per year. Our star outputs about 380 septillion watts. The gap between where we are and where we would need to be is staggering. And here is the layer that compounds the problem. Antimatter cannot be stored easily. It annihilates on contact with any regular matter container. Storing it requires magnetic containment fields that must never fail, powered continuously for decades during a voyage. Any containment failure means the fuel destroys itself, and likely the ship with it. So the picture looks like this. Antimatter offers the physics to potentially make interstellar travel survivable. The production problem may be permanent at any civilization close to our level. And even if you solve production, storage across a multi-decade voyage introduces failure risks that compound daily. For a visiting alien civilization, this means they either found a way past these barriers that we have no framework to understand yet, or they face the exact same wall we do. Both possibilities are strange in their own way. But there is a third option that some engineers took seriously enough to actually develop blueprints for. A design that skips chemical propellant entirely, uses the most violent energy source ever detonated on Earth, and was studied inside actual government facilities with real funding. It involved nuclear bombs, thousands of them, and it got further than you might expect. In 1958, the United States government funded a serious engineering study. The team included physicists who had worked on the Manhattan Project. The idea was direct. Build a large metal plate on the back of a spacecraft. Drop small nuclear bombs behind it at regular intervals. Each blast hits the plate, pushes the ship forward. Repeat thousands of times until you reach interstellar speed. This was called Project Orion, and it ran for years with real money and real scientists, before being effectively ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. The lead physicist on the project, Freeman Dyson, who later became one of the most respected theoretical physicists of the 20th century, calculated that a large Orion vehicle could reach Proxima Centauri in about 130 years, with a crew, with enough mass for serious scientific equipment and life support. 130 years is still multiple human lifetimes, but it sits in a range where generation ship concepts at least become imaginable. The baseline design called for a spacecraft roughly the size of a city block, hundreds of thousands of tons of total mass, a thick pusher plate made of steel and covered in oil to absorb the blasts, nuclear pulse units, small bombs, ejected from the back at a rate of roughly 1 per second during acceleration phases. The design was mechanically straightforward compared to most propulsion concepts, brutally direct. Calculations showed a properly designed Orion vehicle could reach about 10% of light speed with a fuel load that, while enormous, was at least physically gatherable. You would need thousands of nuclear devices. The stockpiles existed. The engineering, while extreme, used known materials and known physics. The team built small conventional explosive test models and flew them. They worked. The pusher plate concept held up. The shock absorption system functioned as predicted. And then the treaty killed it. Detonating nuclear devices above the atmosphere became illegal. Without testing in space, the program could not advance. The blueprints went into archives. Dyson spent the rest of his career convinced that Orion represented the most honest path humanity ever had toward genuine interstellar capability. His personal assessment was that abandoning it pushed the timeline back by at least a century. What Orion reveals about interstellar travel is uncomfortable. The most technically credible propulsion system humans ever seriously developed for reaching another star required detonating around 300,000 nuclear bombs over the course of the journey. That is what the physics demands when you use the most powerful energy sources available within our known engineering range. And even Orion, with all that explosive force, would take over a century to reach the nearest star. No return journey included in most mission profiles. The crew that left would never see home again. A visiting alien civilization would face a structurally identical calculation. If they use physics broadly similar to ours, They need an energy source that makes nuclear bombs look mild. If they have found something genuinely beyond our physics, we have no way to predict what that looks like, or whether it is achievable at all. Orion's legacy is a number you cannot escape. The distances demand speeds. The speeds demand energy. The energy demands a source we cannot currently reach. Every serious engineer who studied this eventually asked the same question. What if the ship itself was the answer? What if instead of carrying all that fuel, you collected energy as you traveled from the interstellar medium itself? That idea produced one of the most elegant and deeply troubled proposals in all of aerospace engineering. In 1960, a physicist named Robert Bussard published a proposal that captured the imagination of every engineer who read it. His idea was elegant. The space between stars is not truly empty. It contains hydrogen, sparse but real, a few atoms per cubic inch on average. Hydrogen is fusion fuel. If a spacecraft could scoop that hydrogen as it traveled and feed it into a fusion reactor, it would never run out of propellant. The ship would accelerate indefinitely, approaching the speed of light, fueled by the galaxy itself. The concept became known as the Bussard ramjet. Science fiction writers loved it immediately. Engineers spent years doing the actual calculations. The scoop would need to be enormous. At interstellar hydrogen densities, collecting enough fuel to run a fusion reactor requires sweeping a circular area roughly thousands of miles across. The magnetic field generating that scoop would need to reach out ahead of the ship, like a funnel hundreds of miles in diameter at minimum. Generating that field requires energy. Running it continuously during a decades-long voyage requires a power source on board just to maintain the collection system itself. Then came the deeper problem. The hydrogen atoms in the interstellar medium are not hydrogen-2, the isotope that fuses most easily. They are ordinary hydrogen proton-only atoms, the hardest kind to fuse. The proton-proton fusion chain that powers stars like ours takes millions of years inside a stellar core to produce meaningful energy. Doing it fast enough, in a compact reactor, to generate net positive power output has never been achieved in any laboratory on Earth. The math revealed a critical flaw. At realistic interstellar hydrogen densities and realistic fusion efficiency estimates, the drag created by the magnetic scoop plowing through the interstellar medium would likely exceed the thrust generated by the fusion reactor. The ship would slow down, not speed up. Subsequent calculations over the following decades confirmed this problem repeatedly. The ramjet, as originally conceived, likely decelerates rather than accelerates once you account for the full drag profile. Engineers proposed modifications. Use the hydrogen collection only for deceleration at the destination. Carry your own fuel for acceleration. Use an improved scoop geometry. Accept a slower top speed and extend the journey time. Each modification addressed one problem and introduced others. What the Bussard ramjet taught the engineering community is a lesson that recurs throughout every interstellar proposal. The interstellar medium is real. The hydrogen is there, and it still cannot be made to cooperate with the energy demands of a ship moving fast enough to be useful. The galaxy between stars is extraordinarily sparse. A cubic mile of interstellar space contains less matter than the best vacuum chamber humans have ever built on Earth. Working with that density, across years of travel, requires either an impossibly large collection system or an impossibly efficient reactor. The two requirements fight each other for mass budget on the ship. For an alien civilization trying to reach Earth, the ramjet scenario would face identical physics. The interstellar medium between their home system and ours is the same sparse hydrogen field. Their scoop geometry problem is our scoop geometry problem. There is one proposal that sidesteps the fuel problem entirely by making the spacecraft so small it barely counts as a spacecraft at all. A project with real funding, real laser hardware, and an engineering team that has published peer-reviewed papers. The question is whether a probe the size of a postage stamp is useful. And the answer depends on what you are actually trying to learn. In 2016, a group of scientists and engineers announced a project called Breakthrough Starshot, with $100 million in seed funding from investor Yuri Milner and backing from Stephen Hawking. The goal was precise: send a probe to Proxima Centauri within a human lifetime. The approach abandoned every conventional propulsion idea. Instead of carrying fuel, the probe would carry none. A ground-based laser array, roughly 1 square mile of coordinated laser emitters, would fire a concentrated beam at a lightweight sail attached to the probe. The photon pressure from the laser would accelerate the sail. Light has momentum, photons push. Solar sails have been tested in space. The concept works. The question was always scale. To reach 20% of light speed, the laser would need to deliver roughly 100 gigawatts of power to the sail surface in a burst lasting a few minutes. 100 gigawatts is roughly the total electrical generating capacity of the United States. Focused on a sail the size of a few square feet, for a few minutes, from a coherent array, all perfectly aligned, the probe itself would be a gram-scale chip. Electronics, a camera, a power source, a transmitter, all packed into something lighter than a paperclip. At 20% of light speed, it would reach Proxima Centauri in about 20 years. The engineering problems are significant and real. The team has published them openly. Atmospheric turbulence distorts laser beams. A ground-based array firing through the atmosphere would lose coherence before the beam reached the sail. Possible fixes involve adaptive optics at a scale never built, or relocating the array to orbit, which multiplies the cost by orders of magnitude. The sail must be extraordinarily reflective. At 100 gigawatts of laser power, a sail that absorbs even a fraction of a percent of that energy vaporizes instantly. Materials with the required reflectivity and structural integrity at gram-scale mass do not currently exist. Pointing precision at that range becomes extraordinary. The beam must track a sail accelerating at thousands of gravities across a distance that grows by thousands of miles per second. Any misalignment, and the sail tumbles, the acceleration stops, and the mission ends. Communication on the return is even harder. A gram-scale transmitter, firing a signal across 4 light-years, would arrive at Earth as a whisper, far below the noise floor of most receivers. The team calculates it is possible with very large receiving dishes, but the bandwidth would be tiny, a few pixels per image maybe, a trickle of data. And the probe cannot stop. It flies through the Proxima Centauri system at 20% of light speed, and keeps going. Total observation window of the target system, roughly 1 hour. Still, Breakthrough Starshot is the most funded, most technically detailed interstellar proposal currently active. Real engineers are solving real sub-problems right now. The sail material research is producing new candidates. The laser ray pointing algorithms are being developed. For the purpose of this mission briefing, Starshot reveals something important. The only technically plausible near-term interstellar mission we can conceive requires a laser ray the size of a city, a probe too small to carry a living cell, no ability to stop at the destination, and 20 years of travel time each way for a data return that might give us a handful of images. An alien civilization sending a similar probe toward Earth would face identical constraints. A chip arriving at our solar system at 20% of light speed, unable to slow down, would pass through our entire system in a matter of hours. We would almost certainly never detect it, which raises a question that has been sitting quietly behind every calculation in this briefing. What if they already sent one? What if it already passed through? And what if the real barrier to contact is something far more subtle than fuel or speed? Every engineering briefing on interstellar travel eventually arrives at a problem that is easy to state and almost impossible to solve. Space looks empty. It is not. The interstellar medium contains dust, microscopic particles, some smaller than a wavelength of light, some as large as a grain of sand, distributed through the void between stars. At everyday speeds, these particles are harmless. A dust grain floating in space is no threat to a spacecraft moving at a few miles per second. At interstellar speeds, the physics changes completely. At 10% of light speed, 67 million miles per hour, a single dust grain with the mass of a sand particle impacts with the energy equivalent to a small explosive charge. A grain of sand. At 20% of light speed, that same grain delivers roughly 4 times as much energy. The impact is not a scratch, it is a punch through whatever material the ship is made of. This is confirmed kinetic physics. Energy scales with the square of velocity. Double the speed, quadruple the impact energy. push to 1/10 of light speed, and the numbers become extreme. A team analyzing the breakthrough Starshot sail design found that even at interstellar hydrogen and dust densities, a sail crossing 4 light-years would encounter thousands of high-energy particle impacts. For a gram-scale chip on a sail, the cumulative erosion from these impacts could degrade the sail material significantly over the journey. The leading edge of the sail would be sandblasted at relativistic speed for 20 years. For a crewed ship, the math is more alarming. A vessel large enough to carry humans, moving at any meaningful fraction of light speed, presents a much larger cross-section to the interstellar medium. Over a multi-year voyage, the accumulated impact energy from dust and particles striking the hull could equal thousands of explosive detonations distributed across the ship's surface. Engineers have proposed shields, a thick block of water ice at the front of the ship, sacrificial material that takes the impact so the crew compartment behind it does not. Calculations suggest that for a trip to the nearest star at 10% of light speed, a water ice shield roughly 10 feet thick would be almost entirely eroded by the time the ship arrived. 10 feet of water, turned to plasma and blown off the front of the ship by particle impacts over 40 years. The shield material itself becomes a problem. Eroding 10 feet of ice generates a spray of secondary particles. Some of those particles fly back and hit the ship. Managing the spray requires additional shielding, which adds mass, which requires more fuel, which takes you back to the rocket equation. There is a deeper issue hiding in this problem. The dust and particle distribution in the interstellar medium is not uniform. Dense molecular clouds, regions where star formation is happening, contain particle concentrations many thousands of times higher than the average void. A ship passing through even the edge of one of these regions would face a sandblasting rate that no proposed shield material could survive. Planning an interstellar route requires knowing the exact dust density along the entire path, 40+ trillion miles of it, in detail precise enough to design a shield that lasts the full journey. We do not have maps at that resolution. We likely cannot get them without sending probes first, which face the same problem. For an alien civilization attempting to reach Earth, the dust hazard along their route is a real engineering constraint. Their path through the galaxy, their local interstellar medium, the molecular cloud distribution between their home system and ours, all of it shapes what shield design they would need. And it means their ship must be built to survive a bombardment that intensifies without warning. They would solve this, or they would not leave. There is no middle ground at relativistic speeds. The bombardment problem compounds with another hazard that the ship generates entirely on its own. A hazard that grows stronger the faster you travel, that cannot be deflected, and that damages living cells at the molecular level. Earth's atmosphere and magnetic field together block the vast majority of cosmic radiation reaching our planet. Standing on the surface, you absorb a small, manageable dose. Astronauts on the International Space Station, above most of the atmosphere but still inside Earth's magnetic field, absorb roughly the yearly radiation limit for nuclear power plant workers in about 6 months. Step outside Earth's magnetic field entirely, as Apollo astronauts did on their way to the Moon, and the dose rate increases significantly. Beyond the field, the galactic cosmic ray environment is unshielded. High-energy protons, helium nuclei, and heavier atomic nuclei stream through the solar system from every direction, remnants of ancient supernova explosions accelerated to near light speed over millions of years. For a crewed ship traveling to another star, this becomes a central survival problem. The journey takes years at minimum. The crew receives full galactic cosmic ray exposure for that entire time, plus additional radiation from their own propulsion system, if it involves nuclear reactions. The most energetic cosmic ray particles, called high-Z high-energy particles, pass through almost any shielding material. They are so energetic that when they hit a dense shield, they generate secondary radiation showers inside the material. A thick lead wall, rather than stopping these particles, creates a secondary spray that can be more damaging than the original beam. This is confirmed by particle physics experiments. NASA has run detailed calculations for a crewed mission to Mars, a trip of roughly 6 months each way with no stops. The estimated radiation dose for that round trip approaches the lifetime limit recommended for astronauts. And Mars is inside our solar system, still partially inside our star's protective bubble called the heliosphere. An interstellar voyage leaves the heliosphere entirely. The journey from our solar system to the edge of the heliosphere, roughly 11 billion miles, has been made only by Voyager 1. Beyond it, the galactic cosmic ray flux increases by roughly 75% compared to Earth's neighborhood. An interstellar crew would live in that elevated flux for decades. A team studying this for a proposed 100-year Starship mission found that with current shielding technology, a crew on a 40-year journey to Proxima Centauri would receive radiation doses far beyond any established safety threshold. Cancer rates, neurological damage, and cellular breakdown across the body would accumulate over the voyage at rates that current medicine cannot adequately treat in deep space. Far from any hospital, the shielding options are limited. Water is a reasonable cosmic ray shield for lower energy particles, and a ship carrying substantial water mass for crew consumption gets partial protection. Hydrogen-rich polymers offer similar partial shielding, but for the highest energy particles, the ones that penetrate anything and generate secondary showers, no passive shielding provides adequate protection. Active shielding, a strong magnetic field generated around the ship that deflects charged particles the way Earth's magnetic field deflects them, is theoretically effective. Generating a field strong enough to deflect high-energy cosmic rays around a ship requires an enormous superconducting magnet running continuously for decades. The power demands, the structural complexity, and the failure modes of that system add layers of engineering difficulty to a mission already straining every other system. For an alien crew making the journey to Earth, the cosmic ray problem is structurally identical. The galactic cosmic ray environment between any two star systems in the Milky Way is the same high-energy flux. Their biology, whatever it is, must survive it. Their shielding must handle it. Any civilization that sends living crew members on interstellar voyages has already solved this problem in a way we have not. That alone implies a technology gap between us and them that goes far beyond rocket design. And the radiation problem only gets worse when you add the physics of what time itself does to the crew during the journey. Because at the speeds required to make the trip survivable in biological terms, time stops behaving the way anyone on the ship or back home would expect. Einstein's special theory of relativity has been tested and confirmed more thoroughly than almost any other idea in physics. One of its core predictions is time dilation. Moving clocks run slow. The faster you move, the slower your clock ticks relative to a stationary observer. At everyday speeds, this effect is real but tiny. The atomic clocks on GPS satellites run slightly fast compared to clocks on the ground because of their orbital velocity and reduced gravity. Engineers correct for this difference in the satellite software. Uncorrected, GPS systems would accumulate errors of several miles per day. At a significant fraction of light speed, the effect becomes dramatic and irreversible. A ship traveling at 90% of light speed experiences time passing at roughly 44% of the rate experienced by a stationary observer. For every 10 years that pass on the ship, roughly 23 years pass back on the home planet. The crew does not feel this. Everything inside the ship feels normal. Their clocks run normally relative to each other. They age at their usual rate from their own perspective, but they fall increasingly out of sync with the rest of the universe. At 99% of light speed, the ratio becomes more extreme. For every year on the ship, roughly 7 years pass outside. A crew traveling at this speed toward Proxima Centauri would experience a journey of less than a year, arriving after 4 years have passed in the rest of the universe. They would be about a year older. Earth would be 4 years older. For an interstellar mission, this creates a profound practical problem. A round trip to Proxima Centauri at 99% light speed, including travel time in both directions, takes roughly 8 years of external time. The crew experiences about 2 years. Everyone they knew when they left is 8 years older. On return, any mission to a star further away compounds this. A round trip to the center of the Milky Way at high relativistic speed could theoretically happen within a human lifetime for the crew. While tens of thousands of years pass on Earth, the crew would return to a planet that had moved through an entire geological epoch since they left. This is not a thought experiment. Muons produced in the upper atmosphere by cosmic ray impacts survive long enough to reach the ground only because time dilation extends their decay lifetime from the perspective of a ground observer. This has been measured directly, repeatedly, in particle physics experiments since the 1950s. Time dilation is as confirmed as gravity. For a civilization planning an interstellar mission, time dilation changes the strategic calculus entirely. Sending a ship at high speed means sending people who will return to a civilization that has moved on without them. The knowledge they bring back may be obsolete. The people they knew may be dead. The civilization that funded the mission may no longer exist in the same form. A round trip to Earth from a star 30 light-years away at 90% light speed would take roughly 67 years of external time. For the crew, about 30 years. If they left with families, those families have aged more than the crew has. The emotional and social disruption of this cannot be managed by engineering. Some researchers propose that time dilation is actually a benefit for one-way colonization missions. A crew that experiences the journey as relatively brief benefits from the speed. But for any mission where the crew intends to return and remain part of their home civilization, time dilation is a wall. An alien crew visiting Earth faces this. If they left their home system decades or centuries of their time ago, centuries or millennia of external time may have passed back home. They would be traveling toward us while their entire civilization aged and changed without them. Communication would take years each way. They would be, in a real sense, alone in the universe for the duration of the journey. And what they find when they reach us might not be worth the cost. But there is a more immediate problem. Getting here fast enough to make time dilation even relevant requires an acceleration phase that imposes forces on the ship and crew that rival the most violent events in the solar system. And stopping once you arrive is, in some ways, harder than leaving. Most discussions of interstellar travel focus on reaching high speed, getting the ship moving fast enough that the journey takes a manageable amount of time. This is the problem that generates the fuel equations, the nuclear pulse concepts. The deceleration problem gets less attention. It should get more. Arriving at Proxima Centauri at 20% of light speed without decelerating means your ship is moving at roughly 134 million miles per hour when it reaches the target system. At that speed, you cross the entire diameter of the target solar system in a matter of hours. Your observation window is measured in hours. You cannot enter orbit. You cannot land. You cannot stop. You pass through and continue on into interstellar space forever. Breakthrough Starshot accepts this. The probe is a flyby mission. It passes through, captures a few hours of data, sends it back over 20 years, and keeps going. For a crewed mission, this is unacceptable. The crew must stop. Stopping requires the same delta V, the same change in velocity, as accelerating. If you burned fuel to reach 20% of light speed, you need to burn the equivalent amount of energy again to slow back down to zero relative to your destination. The rocket equation applies again, with the same brutality. Tsiolkovsky's math says this: if you need a certain mass of fuel to accelerate, and you must carry your deceleration fuel with you from the start, then your starting fuel load must be vastly larger. The fuel you carry to decelerate is dead weight during the acceleration phase, so it costs extra fuel to accelerate that extra fuel. The equations compound. For a round trip, the problem multiplies again. You need fuel to accelerate away from home, fuel to decelerate away from the destination, fuel to decelerate when you return home. Each stage requires carrying all subsequent fuel through all previous stages. The total starting mass becomes enormous. Some proposals sidestep deceleration by using the destination star's gravity or its stellar wind as a brake, arriving on a trajectory carefully calculated to bleed velocity through gravitational interaction, essentially a gravitational capture maneuver. This works for low-speed arrivals, probes approaching at a tiny fraction of light speed. At 10 or 20% of light speed, no stellar gravity well is deep enough to capture a ship. You would need to be moving orders of magnitude slower for gravity to act as a brake in any practical sense. Other proposals involve deploying a secondary sail at the destination. Fire it forward, let the destination star's light push it backward against the ship's direction of travel, using starlight as a brake. This concept, sometimes called a magnetic sail brake, has been studied. The braking force from stellar light pressure at interstellar distances is small, very small. Decelerating a ship with any significant mass in a reasonable time requires a sail area that would make the ship structure impractical. Project Daedalus, the serious 1970s nuclear pulse study, accepted a flyby profile, partly because the deceleration problem had no clean solution within their engineering constraints. A probe that cannot stop at the destination is a probe that provides a few hours of data from 40 light-years away, then disappears. A crewed ship designed by any known engineering method that can also stop at the destination requires a fuel load so large that no proposed production system could supply it in any realistic timeframe. For an alien civilization planning to visit Earth, deceleration is the bill they pay for every mile per hour of speed they gained in acceleration. Their engineering must solve both ends. Whatever propulsion breakthrough they used to accelerate, they used again to stop. And once they have solved stopping, they still have to get here alive. Because the journey itself, at any speed high enough to make deceleration relevant, does something to living biology that no amount of engineering has yet answered cleanly. 6 months on the International Space Station does measurable damage to the human body. Bone density drops. Muscles atrophy from lack of load. The spine elongates. Fluid shifts from the lower body toward the head, increasing pressure on the eyes and potentially causing vision damage. The immune system changes behavior. The cardiovascular system weakens because the heart does not have to work against gravity. 6 months. The best medical monitoring available. Regular exercise protocols for hours per day. The best diet that can be supplied by regular resupply missions. And the damage still accumulates. An interstellar voyage at 10% of light speed toward Proxima Centauri takes 40 years. At 5%, it takes 80 years. Even at the optimistic end of realistic proposals, the journey takes multiple decades in a weightless or near-weightless environment, far from any medical support, with no resupply possible. The bone density problem alone is severe. In microgravity, the body resorbs bone mass because it detects that structural support is no longer needed. Without intervention, a human, in zero gravity, loses roughly 1 to 2% of bone mass per month. Over 40 years, the math is catastrophic. Exercise can slow the loss, but has never fully stopped it in extended spaceflight studies. Artificial gravity offers a solution. Rotate the ship. The centrifugal effect mimics gravity for the crew inside. Engineering teams have designed rotating habitat sections for exactly this purpose. The Orion interstellar proposals included rotating crew sections, a cylinder or ring spinning fast enough to create one gravity on its inner surface is mechanically achievable. The problem is size and rotation rate. For the rotation to feel like natural gravity, without causing nausea, the rotating section must be large. A cylinder, rotating at a comfortable rate, needs a radius of at least several hundred feet to avoid the Coriolis effect, making the crew dizzy every time they move their heads. Smaller radii require faster rotation to achieve one gravity, and faster rotation creates disorienting inner ear effects that persist throughout the mission. Building a rotating section large enough to be comfortable adds structural mass. The connection between rotating and non-rotating sections requires bearings that must function without maintenance for decades. Any failure of the rotation system in deep space cannot be repaired from the ground. Beyond the physical, the psychological load of multi-decade voyages adds its own dimension. Humans, in isolated, confined environments over long periods, develop predictable psychological stress patterns. Depression, interpersonal conflict, loss of motivation, and cognitive degradation have all been documented in Antarctic winter overcruise, submarine deployments, and isolation studies. These are measured in months. Decade-long isolation in a sealed ship with no possibility of rescue or return operates on a different scale entirely. NASA funded isolation studies specifically for long-duration mission planning. Groups of 6 to 8 people in confined spaces over months showed measurable group dynamic deterioration, even with careful crew selection and psychological support. Extrapolating to 40-year voyages with no outside contact requires assumptions about human psychology that no data supports. The combined picture of physical and psychological human limits defines a hard boundary. Any crewed interstellar mission lasting more than a few years requires either a fundamental change in how the human body functions in space, or a method of keeping the crew biologically paused during the journey. That method is called suspended animation. It is the most convenient solution in science fiction and the most stubbornly unresolved problem in real medicine. The appeal is obvious. If you can pause a crew's metabolism, slow or stop the aging process, and wake them at the destination, you solve the journey's duration problem in one move. No psychological deterioration over decades. No bone loss accumulating for 40 years. No food consumption. No air consumption. No crew conflict during transit. The ship becomes an ark. The crew becomes cargo. Real research into suspended animation, or therapeutic hypothermia, as doctors more precisely call it, exists and has produced genuine results. Lowering core body temperature slows metabolism dramatically. Surgical teams use controlled hypothermia to extend the window for complex heart and brain operations, buying time when the patient's circulation is temporarily halted. Some emergency trauma centers use rapid cooling protocols to slow brain damage in patients with catastrophic injuries. These procedures work at temperatures around 50 to 60 degrees Fahrenheit, and for durations measured in hours. Extending them to days or months pushes into uncharted biological territory. The fundamental problem is ice crystal formation. As cells cool, water inside them begins to crystallize. Ice crystals are physically destructive to cell membranes. They puncture and rupture the structures that keep cells functional. At deep hibernation temperatures, every cell in the body faces this damage unless the water is replaced with a cryoprotectant, a chemical that prevents crystal formation. Introducing cryoprotectants at the concentrations needed for deep cooling is itself toxic to cells at higher concentrations. SpaceWorks, an Atlanta-based aerospace engineering firm, received NASA funding to study a mild hibernation concept called torpor for long-duration spaceflight. Their approach does not freeze the crew. It lowers body temperature by about 10 degrees Fahrenheit, enough to reduce metabolic rate by roughly 50 to 70%. Crew members cycle through 2-week torpor periods with brief wake periods. This is biologically closer to the hibernation patterns of some large mammals. Bears and certain ground squirrels can survive months of reduced metabolism without fatal cell damage. The mechanisms they use, including protective proteins that prevent ice crystal formation and metabolic suppression pathways, are subjects of active research. Some teams are working to understand whether these mechanisms can be induced in humans. The honest status is that mild torpor for periods of weeks may become medically achievable within decades. Deep cryogenic suspension, the full freeze and wake cycle popular in fiction, requires solving the ice crystal problem completely and reversibly. No human has ever been successfully frozen and revived. Small organisms have been, some insects, some roundworms. Complex mammalian tissue does not survive with current methods. For a 40-year interstellar voyage, mild torpor could reduce the biological burden of the journey significantly. It does not eliminate food and water needs. It does not eliminate the radiation exposure problem. It does not stop aging entirely, only slows it. For deep cryogenic suspension across a century-long voyage, the biology has not been solved. The gap between what current research supports and what mission plans require is large, measured in fundamental biological challenges rather than engineering details. An alien civilization that travels to Earth in any crude configuration has either solved the deep suspension problem entirely, or they have lifespans that make 40-year voyages manageable, or they travel at speeds fast enough that time dilation collapses the experienced journey duration to something survivable. Each of those options implies something different about what they are, and each one pushes them further from anything we currently understand. The next problem is one that predates the ship design entirely, one that a civilization must solve before they even know Earth is worth visiting. Their information about us, any information they have received, left this planet long before we started sending signals they could interpret. Light travels at roughly 670 million miles per hour. Every signal, every electromagnetic wave, every piece of information about Earth moves outward from our planet at exactly that speed. It cannot move faster. A civilization 4 light-years away, at Proxima Centauri, sees Earth as it was 4 years ago. Not much changes in 4 years. The picture is only slightly stale. A civilization 40 light-years away sees Earth as it was 40 years ago. They see 1985. Ronald Reagan is on their screens. The Berlin Wall still stands. The internet does not exist. A civilization 400 light-years away sees Earth in 1625. European settlers are arriving in North America. Galileo is under house arrest. No radio, no electricity, no technology they could detect. A civilization 4,000 light-years away sees Earth in 2,000 years before the current date. No cities, no agriculture on most of the planet. Scattered human populations living in small groups. A civilization 40,000 light-years away, near the galactic center, sees Earth as it was 40,000 years ago. Homo sapiens exist, but barely distinguishable from the other large primates by any remote observation technology. Radio signals, the only technology we have actually broadcast into space intentionally, have been leaving Earth since the early 20th century. They form a sphere expanding outward at light speed. That sphere currently reaches about 120 light-years in every direction from Earth. Within that sphere, any civilization with a sensitive enough receiver could potentially detect the existence of a technological species on our planet. 120 light-years contains roughly 15,000 star systems, a tiny fraction of the Milky Way's hundreds of billions. Beyond 120 light-years, Earth looks silent, pre-technological, no signals. An alien civilization 600 light-years away sees a planet with no signs of intelligence at all, just oxygen in the atmosphere, and life processes visible in the spectral signature of our air. Interesting, perhaps. Detectable as life-bearing, not obviously worth a multi-thousand-year voyage. Even within our radio bubble, the signals they are receiving are old. A civilization 100 light-years away picking up our earliest radio broadcasts is hearing broadcasts from a century ago. Early television signals, basic radio, weak and dispersed over a century of travel across space. To a civilization building a mission based on these signals, the target is not the Earth that exists now. It is the Earth of a century ago. They cannot know what we have become. They cannot know if we are still here. The light informing their decision left before most people alive today were born. This information lag has a practical consequence for interstellar mission planning. Any civilization sending a ship toward a detected signal source is essentially firing a ship into a future they cannot predict, toward a target that may have changed completely by arrival. A journey of 1,000 years toward a signal they detected means they are arriving at a planet that is 1,000 years older than the version that caught their attention. The universe does not provide real-time intelligence on distant targets. Every interstellar mission is a bet placed on incomplete, out-of-date information about the destination. And yet even this information problem, significant as it is, does not capture the deepest barrier. Because before a civilization can even consider whether Earth is worth visiting, they must survive long enough to build the capability to try. The galaxy is roughly 10 billion years old. Our solar system formed about 4.5 billion years ago. Life appeared on Earth around 3.5 billion years ago. Intelligent, technological life appeared in cosmic terms about a second ago. The galaxy had plenty of time before us. Billions of years during which other stars formed, other planets cooled, and other chemistries had the opportunity to develop the same processes that produced life here. Some of those planets are old enough that a civilization on one of them could have had a billion-year head start on us. A billion-year-old civilization, advancing at even a fraction of the pace humanity has advanced in the last 300 years, should be inconceivably powerful, by any measure we can apply. Their engineering capability would be so far beyond ours that comparing the two would be like comparing a beaver dam to a hydroelectric facility. With 1 billion years, a civilization expanding at a modest pace could colonize the entire galaxy. Researchers have done the calculation, using generation ships traveling at realistic fractions of light speed, stopping at each star system, building infrastructure, launching the next wave. The colonization front spreads across the Milky Way in somewhere between 10 million and 100 million years. Fast by cosmic standards. slow by human lifetime standards, but irrelevant given billion-year timescales. Enrico Fermi famously asked the question in 1950 at a lunch conversation with colleagues: if the galaxy is old enough for this to have happened, and if life and intelligence emerge with any reasonable probability, where is everybody? The silence is real. Confirmed. We have been systematically scanning the sky for radio signals, laser pulses, and other signatures of technology for decades. The search has found nothing confirmed, nothing that passed repeated scrutiny. The sky is quiet. Reframe this as an engineering problem. The interstellar travel barriers we have been walking through in this briefing apply to every civilization in the galaxy, not just ours. The fuel math obeys the same physics everywhere. The radiation environment is the same everywhere. The speed of light enforces the same travel times throughout the Milky Way. If these barriers are genuinely civilization-level hard enough that no species in billions of years has overcome them sufficiently to spread visibly across the galaxy, then the silence makes engineering sense. The galaxy is not full of life-bearing signals, because the step from being alive to being interstellar is almost impossibly large. The physicist Geoffrey West and others have argued that civilizations may tend to collapse before reaching interstellar capability due to resource depletion, warfare, or technological catastrophe. This is a separate filter, one that operates on civilizations rather than on physics. But it compounds the engineering difficulty. A civilization must solve both the technology and the survival problem simultaneously. What Fermi's silence confirms is that either no civilization has overcome these barriers to spread visibly, or they chose not to, or they are here in forms we cannot detect. Each explanation is deeply strange. The engineering interpretation is the most grounded. The barriers are real. They apply everywhere, and the silence may simply be the universe reflecting that reality back at us. But there is one proposal that should, in theory, bypass the speed and fuel barriers entirely. A concept so elegant that if it works, a civilization could fill the galaxy without ever exceeding light speed. And its absence from our skies may be the strangest data point in this entire briefing. In the 1940s, the mathematician John von Neumann developed the theoretical framework for a self-replicating machine, a device that could gather raw materials from its environment, construct a copy of itself, and send that copy onward. Each copy does the same. The population doubles, then doubles again, spreading exponentially. Applied to space exploration, the concept becomes the von Neumann probe, a spacecraft launched to a nearby star system. Upon arrival, it mines the asteroids or moons of that system for raw materials. It builds copies of itself. Each copy launches to a different star system. The process repeats. The math of exponential expansion is extreme, starting with one probe, doubling at each star system, reaching the nearest neighbors first, and spreading outward. A von Neumann probe network could cover every star system in the Milky Way in somewhere between 10 million and 100 million years, even traveling at a small fraction of light speed. A civilization that launched the first probe 1 billion years ago should have probes sitting in our solar system right now. We have not found them. We have searched. Researchers have proposed they might be in the asteroid belt, camouflaged among natural objects. Others suggest they might be in stable orbits around our star, patient, waiting for some condition to be met before activating. The search for extraterrestrial intelligence has considered proposals to look for them specifically. Nothing confirmed. The solar system, examined in increasing detail over centuries, shows no artifact that cannot be explained by natural processes. This absence is profound. A civilization does not need to travel personally to visit every star. They can send a machine that builds itself from local materials. The energy requirements per unit are far smaller than for a crude ship. The risk to biological beings is zero. The timeline, though long by human standards, is short by galactic standards. If even one civilization in the galaxy's 10 billion year history built and launched von Neumann probes, those probes should be here. The mathematics of exponential self-replication leaves no room for them to have missed us. Several explanations have been offered. One is that self-replicating probes are inherently unstable, that errors in replication accumulate, and the system degrades before covering the galaxy. Another is that advanced civilizations deliberately choose not to build them, perhaps fearing exactly the runaway scenario where poorly programmed self-replicators consume every available resource in every system they reach. A third explanation is more troubling. Perhaps civilizations reach the capability to build such probes and are destroyed or choose to withdraw before launching them. A great filter operating at the exact moment a civilization becomes capable of interstellar presence. For the question of alien visits to Earth, von Neumann probes represent the most achievable scenario. A probe launched thousands of years ago, traveling at 0.1% of light speed, could be sitting in our outer solar system right now, watching, having arrived centuries before our civilization became detectable. We would have no idea. The absence of detected probes means either they do not exist, they are here and invisible to us, or they have been here and left. All three options are strange, and all three suggest that the barrier to interstellar presence, whether for crewed ships or self-replicating machines, is higher than it looks from the outside. The last piece of this picture is the one that brings everything back to us directly. Because every engineering barrier we have examined, every fuel equation, every radiation dose, every biological limit, every information lag, every impossibility of self-replicating machinery applies symmetrically. What is hard for them is hard for us. The galaxy may be full of civilizations all looking outward, all running the same calculations, all arriving at the same conclusion. And that conclusion changes what our existence here actually means. Every engineering barrier in this briefing applies to us as well. We are not observers of a problem that belongs to alien civilizations. We are a civilization sitting on one side of the same wall, looking at the same numbers, arriving at the same answers. We have not sent a crewed mission beyond the moon. Our fastest probe, Voyager 1, left the solar system after 47 years of travel and sits roughly 14 billion miles away. It is moving at about 38,000 miles per hour. To reach Proxima Centauri at that speed would take roughly 73,000 years. We are not close to interstellar capability. Every serious proposal on the table, nuclear pulse drives, laser sails, antimatter engines, requires either technology we cannot build yet, or energy infrastructure orders of magnitude beyond what we currently possess. The most optimistic serious timeline for even an unmanned probe reaching another star, something like breakthrough Starshot, is measured in decades of development, followed by a 20-year flight time, followed by a 4-year wait for the data to return. A crewed interstellar mission, by any current or near-future engineering, sits at least several centuries away under the most generous assumptions. What this means for Earth is specific and measurable. There is no cavalry coming. There is no interstellar civilization close enough to arrive in time to matter for any crisis we face on this planet, in any human-relevant time frame. Even if a civilization within 20 light-years detected our distress signals today and launched a ship immediately, traveling at 10% of light speed, they would arrive in 200 years. And the chance that a civilization capable of interstellar travel exists within 20 light-years, is monitoring us, cares about our survival, and is positioned to respond, involves a chain of assumptions that the Fermi silence makes progressively harder to believe. Everything that matters for humanity happens here. The atmosphere, the water, the biosphere, the climate, the genetic diversity, the stored knowledge, the social structures we build, all of it exists on one planet with no backup. There is no interstellar escape route ready to receive refugees. There is no colony ship waiting on a launch pad. The idea that we have an alternative if this planet fails is, by the engineering of interstellar travel, a convenient myth. The same logic applies symmetrically to any civilization trying to visit us. They face the same barriers. Their home world, wherever it is their irreplaceable foundation. The decision to launch an interstellar mission, if they have made it, came after the same calculation we would make. Is the journey worth everything it costs? The physics of interstellar travel do not just explain why we have not been visited. They explain why the universe defaults to isolation. Each civilization, wherever it forms, is surrounded by an enormous, nearly impassable moat of light years. Getting across requires either a technology that may not exist anywhere in the galaxy, or timescales so vast that civilizations must remain stable for geological epochs just to survive the journey's duration. We exist in that moat. All our signals, all our history, all our potential sits inside a bubble 120 light-years across, in a galaxy 250,000 light-years wide. We are not broadcasting into an attentive universe. We are sending letters by firelight into a dark continent that may or may not have anyone positioned to read them. This is confirmed physics, confirmed engineering reality. The distances are measured, the energy requirements are calculated, the biological limits are documented. And sitting with all of that, something shifts in how you see the arguments that usually fill conversations about alien contact. Because the deeper you go into the actual engineering, the more a different kind of question starts to take shape. One that has nothing to do with whether aliens exist, and everything to do with what it would take to survive long enough to ever reach the point where crossing these distances becomes possible. The answer to that question brings us to the most unsettling filter in the entire analysis, one that operates before the rocket, before the fuel, before the launch, one that destroys civilizations from the inside before they ever look up and reach out. In 1998, economist Robin Hanson published a paper that reframed the Fermi silence in a way that has unsettled researchers ever since. He called it the Great Filter. The argument is straightforward. Between simple chemistry and a galaxy-spanning civilization, there are steps. Some of those steps are easy, some are hard. One of them, somewhere in the chain, is so difficult that almost no civilization makes it through. The question Hanson posed is where that filter sits relative to us. Behind us, meaning we already passed through the hardest part, or ahead of us, meaning the hardest part is still coming. If the filter is behind us, the emergence of complex life, or multicellular organisms, or intelligence itself was the rare event. We got through it. We are the exception. The galaxy is mostly empty because the step we already cleared was the bottleneck. If the filter is ahead of us, something kills civilizations after they reach our level of development. Something that happens with near universal reliability to every species that builds radio towers and nuclear weapons and industrial chemistry before they develop the wisdom or the structural resilience to survive what those technologies make possible. The engineering of interstellar travel is directly relevant here. Because the filter, if it lies ahead, likely operates in the window between two specific points. The point where a civilization first gains the capability to cause its own extinction, and the point where it develops the interstellar capability that would allow it to spread beyond a single planet. Humanity entered the first point in 1945, when the first nuclear weapon was detonated. We have not reached the second point. We are in the gap. Every civilization that develops industrial technology goes through a period of rapid energy consumption growth, which means increasing impact on the chemistry of their planet's atmosphere and biosphere. This is not a human-specific pattern. It follows from physics. Energy use and industrialization are linked. Atmospheric alteration from energy use follows from chemistry. Any civilization burning stored carbon compounds for energy on a planet with a carbon cycle will alter that cycle. This is confirmed by basic thermodynamics, not a political claim. The window of vulnerability. The gap between first extinction-capable technology and first interstellar capability may be hundreds or thousands of years wide. A civilization must navigate that window while simultaneously managing the consequences of the same technologies that created its capability. The data from the Fermi silence suggests that navigating this window successfully is extraordinarily rare. Every advanced civilization we might expect to have colonized or signaled by now has either not existed, has existed and collapsed before reaching interstellar capability, or has reached it and deliberately gone silent. For the question of alien visits to Earth, this adds a new dimension. If great filters are common, then advanced civilizations are rare to begin with. Even if interstellar travel were easy, there might be very few civilizations left to attempt it. The physics of travel and the biology of civilizational survival are both working against contact. And here is the dimension that directly affects every person listening to this briefing. If the filter is ahead, we are approaching it right now. The same period that is making us increasingly capable of building interstellar hardware is also the period during which we are most vulnerable to the failures that end civilizations. Climate destabilization, engineered pathogens, nuclear arsenals, artificial intelligence systems with misaligned goals. All of these are products of the same technological acceleration that is our only path toward the stars. We are inside the filter window. Whether we pass through it is not a physics question. It is a choices question. And choices, unlike physics, can change. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for measuring civilizational advancement based on energy use. 3 levels. Type 1 uses all the energy available on its home planet. Type 2 harvests all the energy output of its star. Type 3 controls the energy of an entire galaxy. The scale sounds abstract until you put numbers to it. Our star outputs roughly 380 septillion watts of power every second. Earth intercepts a tiny fraction of that, roughly 1 part in 2 billion. Of that intercepted fraction, humanity currently uses about 10 trillion watts annually. We are not yet a Type 1 civilization. By Kardashev's numbers, we sit around Type 0.7. We use a fraction of our own planet's available energy. A Type 2 civilization harnesses all 380 septillion watts from their star. The difference between us and them is not a multiplier. It is many orders of magnitude of energy production, a gap so enormous that the comparison has no intuitive anchor. Why does this matter for interstellar travel? Because every serious interstellar propulsion system requires energy at scales that only a Type 2 or near Type 2 civilization could supply. Antimatter production, as calculated earlier, requires enormous fractions of a star's energy output just to produce fuel for a single mission. A nuclear pulse-drive ship large enough to carry a crew to another star requires thousands of nuclear devices and a construction and launch infrastructure of planetary scale. A breakthrough Starshot laser array requires roughly the total electrical output of the United States for a few minutes per launch. Scaling any of these to a crewed mission capable of surviving the journey and stopping at the destination pushes the energy requirements into the Type 2 range. This means that a civilization capable of interstellar travel must have already solved the energy problem at a civilizational scale. They are not burning fossil fuels. They are not at the beginning of their renewable energy transition. They have full stellar energy capture, a Dyson sphere, a Dyson swarm, a dense network of solar collectors, fully enclosing their star, or some equivalent structure. A Dyson sphere, the most commonly cited Type 2 megastructure, would completely enclose a star and capture its entire output. The material requirements are extraordinary. Disassembling every rocky planet in a solar system would provide the raw mass to build one. The engineering is, by our current standards, completely out of reach. And yet in 2015, the star known as Boyagin's star, a relatively ordinary star about 1400 light-years from Earth, began showing brightness dimming patterns unlike anything previously observed. The light curves were irregular, deep, and asymmetric in ways that natural explanations struggled to fit cleanly. Some researchers proposed a partial Dyson structure, a swarm of megastructures in construction, as a hypothesis. The hypothesis was taken seriously enough to generate follow-up observation campaigns. Subsequent data collection has pointed toward natural explanations, clouds of dust and debris being the current leading candidate, not confirmed to be artificial. But the fact that the hypothesis was scientifically plausible enough to investigate says something about where our collective imagination now sits. A Type 2 civilization exists, in energy terms, on a scale so far beyond ours that their ship design, their fuel sources, and their engineering methods likely bear no resemblance to anything we have conceived. Recognizing their spacecraft as a spacecraft might be as impossible as asking someone from the Bronze Age to recognize a satellite, and that possibility that we might have already been visited by something we could not identify as artificial sits behind the next question. A question about what a real interstellar ship would actually look like, and whether we would have any idea. Every depiction of alien spacecraft in popular culture reflects human engineering intuitions: propulsion at the back, crew compartment in a pressurized hull, navigation systems we can imagine, a shape that suggests aerodynamics even in space, where aerodynamics do not apply. Real engineering constraints push interstellar spacecraft design toward forms that follow function, in ways we have not seen and may not immediately recognize. Consider shielding. A ship traveling at a significant fraction of light speed needs to protect against particle bombardment, from the front. The optimal shape for minimizing cross-section while maximizing interior volume might be a narrow cone or a needle, with all habitable space tucked behind a deep forward shield. From the side, such a ship would look like a spike or a rod, nothing resembling any spacecraft we have built. Consider radiation shielding for the crew. Surrounding the crew compartment with the densest available material, water tanks, fuel reserves, or heavy metals reduces cosmic ray exposure. A ship designed around this priority might look like a sphere with the crew buried at its center, surrounded by layers of material. No visible engine bell, no visible windows, a dense, featureless ball. Consider a laser sail configuration at interstellar cruise. A sail potentially miles across, gossamer thin, attached to a tiny payload at the trailing edge. Moving at 20% light speed in deep space, it would be essentially invisible to any telescope not specifically pointed at it and calibrated to detect its reflectivity. Consider a ship designed for multi-generational travel. It must sustain a closed ecosystem for decades or centuries. The biological and agricultural systems require volume. The structure might look more like a rotating habitat cylinder, hundreds of feet across, surrounded by shielding material, than like any vessel we associate with spacecraft. From a distance, it might be indistinguishable from a large asteroid on an unusual trajectory. The objects we search for when we scan for alien spacecraft are objects shaped by our own engineering intuitions: a metallic reflection, a controlled trajectory, a radio emission pattern suggesting electronic systems. But a civilization with different materials, different power sources, and different design philosophies might produce objects that our detection systems classify as natural. The interstellar object known as Oumuamua, detected in 2017 on a trajectory that came from outside the solar system, showed characteristics that were unusual enough to prompt serious scientific discussion about whether it could be artificial. Its shape, inferred from its brightness variations, appeared elongated far beyond any known natural asteroid. Its acceleration as it left the solar system was slightly higher than solar radiation pressure alone could explain. The leading scientific explanations are natural, thin hydrogen ice or nitrogen ice, explaining both the shape and the anomalous acceleration. The scientific community has not concluded it was artificial, but the discussion was serious, peer-reviewed, and ongoing. If an artificial probe passed through our solar system, and we could not determine with certainty that it was artificial, then interstellar contact may have already happened in a form we lacked the tools to confirm. This is not a confirmed fact. It is a real possibility with real scientific weight behind it. What it implies is that our search methods, calibrated to find things that look like us, may systematically miss things that look like a civilization operating at a completely different technological level. The filter on alien detection may be in our own eyes, not in the absence of visitors. But even granting all of this, there is one problem that no amount of advanced engineering resolves cleanly, a problem baked into the geometry of navigation across light years. Stars move, they orbit the galactic center. They drift relative to each other at speeds of tens of miles per second. From our solar system, these motions look small because the distances are vast. But over the timescales relevant to interstellar travel, stellar drift becomes a significant navigation problem. Proxima Centauri, at its current rate of motion, moves far enough across the sky over 1,000 years that the direction you would need to aim a ship changes measurably. A ship launched today toward where Proxima Centauri appears to be would arrive at empty space if the journey took hundreds of years, because the star will have moved. For a journey of decades, this is a correctable error. A ship traveling 40 years can take navigational readings throughout the voyage and adjust course as the destination's actual position becomes clearer. This requires active navigation systems functioning for 4 decades without failure, fuel reserves for course corrections, and communication with a home base whose navigation data is increasingly out of date the further the ship travels. For a journey of centuries, the required aim adjustment at launch becomes substantial. A ship leaving a star system 100 light-years from Earth, aimed at where Earth appears from their telescopes, is aiming at where Earth was 100 years ago. By the time they arrive, another 100 years have passed. The total stellar drift error could place the ship off target by a significant fraction of an astronomical unit, hundreds of millions of miles. Add to this the proper motion of both the origin and destination systems, and the calculation becomes a prediction problem. The navigators must model the gravitational interactions between multiple stellar bodies over the full journey duration and predict where the target will be upon arrival, not where it appears to be when they aim. This is solvable in principle, but it requires long Vaseline observation of the destination's motion before launch. Building an accurate proper motion model for a distant star system requires tracking it over decades to centuries. An alien civilization preparing to visit our solar system would have needed to observe us for a very long time before they could calculate the precise heading required for a successful arrival. That sustained observation period, before any ship launches, represents a significant commitment. They would need to decide we were worth watching for generations before deciding we were worth visiting. And the navigation problem compounds once the ship arrives. Entering a solar system at significant velocity requires precise deceleration targeting. Coming in too fast, aimed slightly wrong, means passing through the outer system without the ability to correct before flying out the other side. The precision required for a successful interstellar arrival, factoring in stellar proper motion over centuries of travel time, and the deceleration targeting needed for a controlled approach, is beyond any navigation system we have built. It is achievable in principle, given sufficient computational power and propulsion authority for corrections, but every layer of required precision adds engineering complexity that must function perfectly throughout the journey. A civilization that arrived here successfully solved all of this, every piece of it, and they aimed for a planet that, from their perspective, they had been watching through a telescope for a very long time, seeing a version of it that was already centuries old by the time they launched. The gap between deciding to come and actually arriving is so long that whatever they hoped to find here may have already changed beyond recognition. The space between stars contains matter, sparse, cold, mostly hydrogen and helium, with trace amounts of heavier elements and dust grains. The average density is roughly 1 atom per cubic inch, far less than the best laboratory vacuum ever created on Earth. By any everyday measure, it is essentially nothing. At interstellar speeds, it becomes a serious engineering problem. A ship, moving at 10% of light speed 67 million miles per hour, hits each interstellar hydrogen atom with the kinetic energy equivalent to a tiny but real impact. Individually, each atom does essentially nothing to a large ship. Collectively, over years of travel through billions of cubic miles of this sparse medium, the accumulated effect is measurable erosion. The leading edge of the ship, whatever material faces forward into the interstellar medium, takes the continuous bombardment. At 10% of light speed, hydrogen atoms arrive at the ship's surface, with enough energy to knock atoms loose from the hull material. This process is called sputtering, and it is well understood from semiconductor manufacturing, where ion beams are used to precisely erode material surfaces. In manufacturing, it is controlled and useful. On an interstellar ship, it is unavoidable damage. Over a 40-year journey at 10% of light speed, the sputtering erosion on exposed hull material could remove significant layers from the leading surface. The rate depends on the material. Diamond-like carbon coatings, which are exceptionally hard and resistant, would still erode measurably. Soft metals, or conventional spacecraft aluminum, would erode far faster. Beyond sputtering, the interstellar medium contains a component called the interstellar magnetic field, a weak but pervasive field that threads through the space between stars. A ship with active magnetic shielding for cosmic ray protection interacts with this field in complex ways. The drag effects are small, but real over long timescales. The interstellar medium also varies in density. The region of space within about 300 light-years of our solar system sits inside what astronomers call the local bubble, a region of lower than average interstellar density, carved out by ancient supernova explosions. The average density here is lower than typical galactic interstellar space. Beyond the local bubble, densities increase. An alien ship traveling from outside the local bubble toward Earth would have passed through denser interstellar medium for most of its journey, then entered the relatively clear local region in the final approach. Their shielding design would need to handle the denser regions without being overbuilt for the final leg. Denser interstellar regions exist, where molecular clouds form, where star formation is active, and where supernova remnants have compressed the medium. A ship crossing any of these regions at interstellar speed would face sputtering rates and particle bombardment far higher than the average. Planning an interstellar route requires mapping the density profile of the entire path and designing the ship to survive the worst sections. We do not have density maps of the interstellar medium at the resolution needed for this kind of route planning. We have broad surveys, average values, and general structure. The fine detail of a specific 40 light-year path, the density variations meter by meter over trillions of miles, is beyond current observational capability. An alien civilization preparing a mission to Earth would face the same mapping limitation unless they had already sent probe missions to survey the route. And sending probes to survey the route is itself an interstellar mission requiring the same propulsion and survival engineering as the crewed mission it would precede. The interstellar medium asks a question before every mission: have you mapped me well enough to survive me? And the only honest answer, with current or near-future technology, is no. The concept of a generation ship appears regularly in interstellar mission proposals as the fallback when all faster propulsion options fail. If you cannot make the journey fast enough for a single crew to survive it, send a ship large enough to sustain a population across multiple generations. The original crew's grandchildren, or great-grandchildren, arrive at the destination. The appeal is that it sidesteps the propulsion problem. You do not need high speed, you need sustainability. The engineering requirements for a generation ship are, in many ways, harder than for a fast ship. A fast ship must protect its crew for decades. A generation ship must sustain a civilization for centuries. Food production for a closed ecosystem over centuries requires a complete agricultural system running inside a sealed environment. With no external inputs after departure, every nutrient cycle must close. Carbon dioxide exhaled by the crew becomes plant food. Waste from crops and crew goes back into the soil. Water cycles continuously through transpiration and condensation. This is called a closed-loop life support system, and we have never built one that runs without external inputs for more than a year or two. The longest continuous isolation experiment involving human populations and closed life support, the Biosphere 2 project in Arizona in the early 1990s, required emergency oxygen injection from outside within a year and ultimately failed to maintain the intended closure. Genetic diversity for a viable population. Across multi-century isolation, geneticists have calculated that a population below roughly 500 individuals risks inbreeding depression over generations, where rare, harmful genetic variants become common because the gene pool is too small. Some estimates push the viable minimum higher, toward 2,000 individuals, depending on assumptions about genetic management. Carrying 2,000 people in a space-traveling closed ecosystem for 300 years requires a structure of enormous mass. The habitat volume alone, at livable densities, demands a ship larger than many city blocks. The agricultural systems add more volume. The shielding mass adds more. The propulsion system to move all of this adds more. The social engineering problems dwarf even the physical ones. A population of 2,000 people with no possibility of outside contact, governed by rules that cannot evolve through normal social mechanisms across 12 or 15 generations, must somehow remain cohesive and mission-focused. The mission goal, arriving at a destination none of the living crew chose, and none of them will experience in their own lifetimes, must somehow remain motivating to people born in transit. History provides no examples of social structures maintaining stable purpose across 15 generations without external input. Religions and dynasties have lasted that long, but always with contact to outside populations, trade, conflict, and cultural exchange that kept them dynamic. A generation ship has none of these inputs. The middle generations born mid-journey will never know a planet. They will never experience open sky, wind, the variety of a natural ecosystem. They inherit a mission chosen before they were born, bound for a destination they will never reach, leaving a home they never knew. Maintaining psychological health and social cohesion across those generations is a problem with no tested solution. A civilization that has successfully sent generation ships has already solved all of this. Their social science, their life support engineering, their genetic management, and their psychological frameworks for multi-generational mission coherence are all functioning at a level we cannot claim. The fact that we know how hard this is makes any civilization that accomplished it more impressive and more alien to us, not less. The physicist Liu Cixin, in his novel series, described a universe where every civilization capable of interstellar travel faces the same strategic calculation. Resources in the universe are finite. Any civilization that reveals its location to another risks being destroyed by that civilization before it can be perceived as a threat. The only safe strategy is silence and preemptive elimination of any detected civilization. This is called the dark forest theory, and while it originated as science fiction, it has been discussed seriously in academic papers on the Fermi paradox since the book's publication. The logic is cold and consistent. Two unknown civilizations detect each other across interstellar distances. Each knows the other exists but cannot know the other's intentions. The time lag in communication means by the time a signal is received and a response sent and received, decades or centuries have passed. A civilization cannot negotiate in real time across light years. It can only act on the information it already has. Given that resources are limited and that a technologically aggressive civilization could eliminate a detected rival, the rational preemptive move from a pure game theory standpoint may be elimination. The implications for the question of alien visits to Earth are disturbing in a specific way. We have been broadcasting radio signals for over 100 years. Our radio bubble now extends 120 light years in every direction. Any civilization within that sphere, with sensitive enough receivers, knows we are here. They know we are technological. They have several decades of our broadcast history to analyze. If the dark forest hypothesis describes the dominant strategic posture of advanced civilizations, then our broadcasts have already alerted potential threats to our location. The absence of a response, in this framework, is hopeful. Silence means no one within range has decided to act, or has not yet detected us, or is too far away for their response to have arrived. The dark forest theory is not confirmed, it is a hypothesis. The alternative, the zoo hypothesis, proposes that advanced civilizations are aware of us and have chosen not to interfere, perhaps watching our development the way a naturalist observes wildlife. In this model, the silence is deliberate non-contact, not absence or threat. Both hypotheses share a common feature relevant to this briefing. They assume civilizations capable of interstellar travel exist and have made active choices about us. The engineering barriers we have examined suggest those civilizations, if they exist at all, are extraordinarily rare. A third interpretation sits between the others. Perhaps the silence reflects civilizations that looked at the same engineering barriers described in this briefing, ran the same calculations, and concluded that interstellar contact is so costly and so slow that it simply does not happen, regardless of strategic preference. The universe is not dark because everyone is hiding. It is quiet, because traveling and communicating across light years is hard enough that no one has managed it at scale, regardless of intentions. This third interpretation is the one most consistent with the physics, and it carries its own specific implication for Earth. Our signals are out there. They cannot be recalled. The decision to broadcast was made before anyone calculated the full strategic implications of announcing our location to an unknown galaxy. Whether that matters depends on which interpretation is correct, and we have no way to know. Radio silence from the cosmos has been interpreted many ways. Perhaps other civilizations do not use radio. Perhaps they have shifted to more efficient communication methods. Perhaps they are deliberately quiet. But there is a more fundamental explanation that the physics supports directly. Sending a detectable signal across interstellar distances requires extraordinary power. Our most powerful radio transmitters on Earth broadcast at roughly 1 million watts. That sounds large. At the distance of Proxima Centauri, that signal has spread across a sphere so vast that any receiving antenna picks up an almost immeasurably small fraction of the total power. The signal falls below detectable noise levels within a few light years of Earth, for any realistically sized receiver. The Voyager 1 spacecraft, now beyond our solar system, transmits at 23 watts. The signal reaching Earth across 14 billion miles requires a receiving dish 70 meters in diameter just to detect. Voyager's signal across 4 light years would be completely undetectable with any antenna currently on Earth. To be detected across tens of light years with any receiver smaller than a city, a transmitter must broadcast at power levels in the billions or trillions of watts, and do so continuously and in a targeted direction. This is within the theoretical range of a civilization significantly more advanced than us, but represents an enormous energy expenditure for ongoing communication. This is the same energy problem that faces propulsion, appearing again in a different form. Whether you are trying to move mass or move information across light years, the distances impose energy costs that civilizations at our level cannot sustain. The search for extraterrestrial intelligence has been monitoring the sky for unusual radio signals since 1960. In decades of systematic observation, covering billions of frequency channels and billions of square degrees of sky, the search has found one candidate signal of interest, the WOW signal of 1977, which matched theoretical profiles of an interstellar broadcast, but was never repeated and was never confirmed. One candidate in decades of searching, never confirmed. The sky is quiet. The energy interpretation says this is expected. Civilizations broadcasting at the power levels needed for casual interstellar communication are broadcasting at Kardashev Type 2 power levels, or beyond. There may be very few of them. The ones that exist may be broadcasting directionally, targeting specific stars they have identified as interesting, rather than broadcasting in all directions. A directed broadcast aimed at a different star system would be invisible from Earth, unless we happen to be in the beam. We are likely not special enough from the outside to be specifically targeted by any directed broadcast that has already been sent. Our radio bubble is young and faint. Our signals are a whisper. If a civilization is listening for us specifically, they have been doing so on very little signal for a very short time. The practical implication is that interstellar communication, the precursor to interstellar contact, faces the same energy wall as interstellar travel. Both require either far more power than we currently produce, or a patience measured in centuries. For civilizations attempting to reach us or speak to us, the effort scales with distance in a way that makes casual contact essentially impossible. Contact, if it comes, will be deliberate, expensive, slow, and based on information that is already old by the time it arrives. General relativity, Einstein's theory of gravity, is the most precisely tested physical theory in history. Its predictions have been confirmed to extraordinary precision, from the bending of light around massive objects to the detection of gravitational waves from colliding black holes 1 billion light-years away. It is our best description of how space, time, and gravity work. And within that confirmed, thoroughly tested theory, the mathematics permits some strange structures. A wormhole is a theoretical tunnel connecting two distant points in spacetime. If a stable wormhole could be created and held open, a ship entering one end could emerge from the other end at a different location, potentially bypassing the need to travel the distance between them. The mathematics of general relativity has allowed wormhole solutions since 1935, when Einstein and Nathan Rosen first described what they called Einstein-Rosen bridges. The problem is stability. A wormhole that forms naturally, if any do, would collapse almost instantly due to its own gravitational dynamics. Keeping one open long enough to pass anything through requires negative energy, a form of energy that pushes outward against gravity, rather than pulling inward. Negative energy is real. The Casimir effect, a measurable quantum mechanical phenomenon where two metal plates very close together experience a tiny attractive force due to quantum fluctuations in the vacuum between them, demonstrates that regions of negative energy density can exist. This is confirmed by experiment. The quantity of negative energy needed to hold open a wormhole traversable by a spacecraft, however, is enormous. Calculations suggest you would need negative energy equivalent to the mass energy of a large planet, concentrated precisely along the wormhole throat, and maintained indefinitely. The Casimir effect produces negative energy densities far too small and in geometries far too restricted to approach this requirement. Warp drives fare similarly. Miguel Alcubierre proposed a metric in 1994, describing a space-time configuration where space itself contracts ahead of a ship and expands behind it, carrying the ship forward faster than light, while the ship itself remains stationary relative to its local space. The math is consistent with general relativity. The energy requirements involve negative energy densities comparable to or exceeding the total mass energy of the observable universe. Later, refinements have reduced the requirement, but the exotic matter problem remains unsolved. Neither wormholes nor warp drives have been observed. No naturally occurring wormhole has been detected anywhere in the universe, despite extensive surveys. No warp drive signature has been detected. Both remain mathematical possibilities within a well-tested theory. For an alien civilization, these structures represent either a path they cannot use, because the negative energy problem is as unsolvable for them as for us, or a path they have found through physics beyond our current framework. The second option is coherent but currently unprovable. We have no theory that predicts how negative energy at the required scales could be generated. The honest status is this: wormholes and warp drives are mathematically permitted by the same equations that predicted gravitational waves, black holes, and time dilation, all of which turned out to be real. They may therefore be real possibilities. They require conditions, specifically negative energy at extreme scales, that nothing in our observational history of the universe has ever shown to exist naturally or artificially. They are the most seductive shortcuts in all of physics, and they remain, for now, speculative in the most specific sense. Theoretically permitted, observationally undetected, technologically unreachable. If aliens arrived through one, they know something about the universe that we have not yet discovered. And that gap in knowledge would be among the largest we could possibly imagine. Our solar system spans roughly 2 light-years from the central star to the outermost edges of the Oort cloud, the vast shell of icy bodies at the system's boundary. The inner solar system, where the rocky planets orbit, fits within a sphere about 5 astronomical units, across roughly 5 times the Earth-to-star distance on each side. A ship could enter the inner solar system and approach Earth without being detected, unless we happen to be pointed at it. Our current planetary defense systems scan primarily for near-Earth asteroids, objects that cross or come close to Earth's orbit. They survey a fraction of the sky repeatedly, and flag objects that move against the background star field in patterns consistent with solar system objects on specific trajectories. A ship on an interstellar approach trajectory, decelerating into the solar system at fractions of light speed, would move across the sky at a rate unlike any known natural object. It would be bright in certain wavelengths and dark in others depending on its surface material and temperature. If it was designed to minimize radar cross-section or optical reflectivity, it could be effectively invisible to current surveys. The Space Surveillance Network, operated by the United States military, tracks roughly 50,000 objects in Earth orbit with high reliability. Objects in deep space beyond a few million miles are tracked far less systematically. Telescopes like Pan-STARRS and the Vera Rubin observatories survey the sky for moving objects, but their detection limits at great distances depend on the object's size and reflectivity. Oumuamua was detected as it was already departing the solar system after its closest approach to our star. It was inside the solar system before we knew it existed. A second interstellar object, a small comet designated Borisov, was detected before its closest approach, but only because amateur astronomer Gennady Borisov spotted it while conducting a personal sky survey. 2 interstellar objects detected in recent decades, both natural, neither detected early in their approach. The detection window was narrow in both cases. A probe or ship arriving on a carefully planned trajectory, possibly designed to approach from a direction away from our concentrated survey coverage, could potentially enter the inner solar system without triggering any current detection system. This is not a confident assertion. It is a real gap in our observational coverage that astronomers acknowledge. Active search programs have been proposed specifically to look for anomalous objects in the solar system. Objects on non-Keplerian trajectories, objects with unusual spectra, objects accelerating in ways inconsistent with solar radiation pressure alone. These programs have not been fully funded or implemented. If an alien probe arrived in our solar system in the last century, and we were not specifically looking for it, the probability that we detected it is low, not zero, low. This is confirmed by our actual detection record. Oumuamua passed through, and we almost missed it. The solar system is large. Our surveys are incomplete. The question of whether we have been visited is partly a question of whether we have been looking carefully enough for long enough. And the honest answer is that we have not been looking for very long, with instruments adequate to the task, systematically. Whatever answer the universe holds on this question, we are still in the early stages of being able to check. Every barrier discussed in this briefing, radiation damage, psychological deterioration, bone loss, food requirements, genetic diversity thresholds, time dilation's effects on social continuity, all of these apply specifically to biological organisms, to creatures made of cells that require oxygen, water, food, and protection from radiation to survive. A civilization that has developed artificial general intelligence, or that has transitioned its consciousness into a non-biological substrate, faces a fundamentally different set of engineering constraints. A silicon or photonic processing system does not experience bone loss in zero gravity. It does not develop psychological deterioration from isolation. It does not require food production or atmospheric recycling. It can be designed to be radiation hardened by material selection rather than by shielding mass. It can be switched off during transit and reactivated at the destination, sidestepping the entire passage of time during the journey. The timeline from our current technological level to artificial general intelligence is debated intensely within the research community. The timeline from artificial general intelligence to digital substrate transfer of human equivalent consciousness is even more uncertain. The philosophical questions about whether transferred consciousness retains continuity of identity are unresolved and deeply contested. But the engineering implications are clear. A civilization that has solved these problems, even partially, could send interstellar travelers that are not biological in any conventional sense. A hard drive containing the patterns of a mind, a robotic body capable of operating in vacuum, a processing system designed to restart after decades of cold storage. This entity would survive the journey, endure the radiation, require no food, produce no waste, and need no psychological management. Several researchers have proposed that the first interstellar travelers from Earth, if any ever launch, will be artificial minds rather than biological ones. The energy and mass savings of removing life support from a mission profile are enormous. A ship carrying only digital minds and robotic bodies could be far smaller and faster than any crewed biological mission. For an alien civilization, the same logic applies with greater force. A civilization millions of years older than ours has had time to develop and refine non-biological intelligence to a degree we cannot predict. An interstellar probe from such a civilization might carry no biological life at all. It might be indistinguishable in construction material and behavior from a sophisticated autonomous system, a robot making decisions based on programmed goals, rather than a being with consciousness in any sense we would recognize. This possibility makes the detection problem harder still. We tend to assume that contact with an alien civilization would feel like contact with another mind, communication, signal exchange, some form of recognition. Contact with an autonomous robotic probe, operating on goals set by a civilization that may have launched it thousands of years ago, might feel like encountering a very unusual machine. If any alien presence has visited this solar system, it may have been in exactly this form, and we may have filed whatever we detected under the category of anomalous natural phenomenon because we were not equipped to ask the right question. Picture the view from a planet 3,000 light-years away. Their astronomers, if they exist, point their telescopes at our star and see a small rocky planet with oxygen and water in its atmosphere. Biosignatures. Interesting. Life, probably. Intelligent, technological life. No evidence of that at all. The light-carrying evidence of our civilization has traveled a maximum of 120 light-years from Earth. Radio silence beyond that. Our star, from 3,000 light-years away, looks like an unremarkable yellow dwarf with a biosphere. Worth noting in a catalogue, probably not worth a 3,000-year voyage. This matters for the alien visitation question in a specific way. Any civilization beyond 120 light-years cannot yet know we are technological. They see a planet with life, which is interesting, but arguably not unusual enough to warrant the engineering cost of an interstellar mission. Civilizations within 120 light-years that have detected our signals face an information lag. A civilization 100 light-years away is receiving our signals from 100 years ago. Early radio. Weak, unfocused, barely above noise. Building a mission plan based on early 20th century radio leakage would require enormous investment for a target that, from their view, might represent an early industrial civilization, still using fossil fuels and incapable of interstellar communication. Whether that seems worth visiting depends on their goals. Scientific interest in a young technological civilization? Possibly. Resource acquisition? Our star system does not have resources unavailable elsewhere closer to them. Strategic concern about a growing technological civilization? Perhaps in a dark forest scenario, but we are still far too weak to represent any credible threat. The honest calculus, from an alien perspective, argues against a visit specifically to Earth at this moment in our development. The signal we are broadcasting says we exist and are young. It does not say we have something irreplaceable. The journey cost is enormous. The information return on a multi-century voyage to observe an early industrial species may not justify the mission. This may be among the most grounded explanations for the absence of detected contact. We are not yet interesting enough, from far enough away, to be worth the engineering commitment an interstellar mission requires. A civilization that did decide to visit, despite this calculation, would be either extremely curious, extremely cautious about our growth trajectory, or operating under a motivation we cannot predict from our current position. Each of those is possible, and each says something different about what contact would look like if it came. Every calculation in this briefing has assumed one universe, one set of physical laws, one expanding spacetime containing all the matter and energy there is. Several well-supported theoretical frameworks in physics suggest the actual picture is more complex. Cosmic inflation, the rapid expansion of spacetime in the first fractions of a second, after the Big Bang, predicts in many of its versions that inflation did not stop everywhere at the same time. Different regions of spacetime exited the inflationary phase at different times, each becoming its own separate expanding universe, each potentially with different physical constants. This is the eternal inflation model, and it is taken seriously by a significant portion of the cosmological research community, though it remains unconfirmed, and perhaps unconfirmable by any experiment we can currently design. If true, our observable universe is one bubble in an enormous, possibly infinite collection of universes. Other bubbles are causally disconnected from ours. No signal, no ship, no particle can pass between them. The separation is not like the separation between star systems, bridgeable in principle with enough energy and time. It is a causal disconnection built into the structure of spacetime. Other universes, if they exist, are permanently inaccessible. String theory, another major theoretical framework in physics, predicts the existence of extraspatial dimensions, compactified at scales too small to detect with current instruments. Some versions of string theory produce a landscape of possible universes, each with different physical constants, each inaccessible from the others. The many worlds interpretation of quantum mechanics, which some physicists accept as the most coherent reading of quantum measurement results, suggests that every quantum event branches reality into separate versions. These branches are not separate universes in the same sense as inflation bubbles. They are different branches of the same quantum wave function, diverging and non-interacting. What all of these frameworks share, if any of them correctly describes reality, is a vast increase in the total number of contexts where civilizations might exist, and an equal increase in the number of those contexts that are forever inaccessible to us. Alien civilizations in other inflationary bubbles, if they exist, are irrelevant to the question of visiting Earth. The causal disconnection is permanent and absolute. Our searches, our signals, our ships, none of it reaches them, and none of theirs reaches us. This does not help explain the Fermi silence within our own observable universe, but it adds a layer to the total picture of why alien contact may be impossible. The universe we can access may be a small fraction of all the realities where something interesting might be happening. We are searching in one bubble among what may be infinite bubbles, with instruments that only work inside our bubble, looking for neighbors who are almost certainly also inside their own bubbles, most of which we can never see. The silence of our sky may be as much a geometry problem as a biology problem. The zoo hypothesis was proposed in 1973 by radio astronomer John Ball. His argument was that the galaxy may be populated by advanced civilizations that are fully aware of Earth and have made a deliberate collective choice to observe without interfering. We are, in this picture, in a nature preserve. The silence is not absence, it is policy. The idea has a certain appeal because it resolves the Fermi silence without requiring that interstellar travel be impossible. Advanced civilizations exist. They can travel here. They have chosen not to, or to keep their presence invisible. The engineering and coordination problems with this hypothesis are significant and underappreciated. For the zoo hypothesis to explain the complete silence, every civilization in the galaxy with interstellar capability must maintain the non-interference policy. Every one of them, across billions of years of galactic history. A single rogue civilization, a single expedition that decided the policy was unnecessary, a single explorer that disagreed with the consensus, would have broken the silence at some point in 4 billion years of Earth's history. There would be evidence. Maintaining a perfect, galaxy-wide consensus across independent civilizations with different histories, different biologies, and different values, over timescales that dwarf the entire history of human civilization, requires a coordination mechanism so robust that it has never failed even once. We have no framework for what that mechanism would look like, or why it would hold indefinitely. Some versions of the hypothesis propose that the supervising civilizations actively enforce the policy, eliminating any rogue actors before they break the silence. This version quickly becomes the dark forest hypothesis in a polite dress. Other versions propose that sufficiently advanced civilizations converge on non-interference as an ethical universal, that any species wise enough to achieve interstellar capability also recognizes the importance of letting younger civilizations develop independently. This is coherent as an aspiration, but has no supporting evidence, and requires that every civilization reaches the same ethical conclusion, without exception. The simplest objection is probabilistic. Given the range of motivations humans alone demonstrate, the variety of values, the history of groups acting against collective agreement for individual or factional benefit, projecting absolute consensus onto billions of civilizations across billions of years, requires an assumption about the behavior of intelligence that nothing in our experience supports. The zoo hypothesis is elegant. It is philosophically appealing. It is almost certainly too coordinated to be the actual explanation for the silence. A more uncomfortable explanation sits in the gap between the zoo hypothesis and the dark forest, a universe where advanced civilizations are genuinely rare, interstellar travel is genuinely hard, and the silence is simply the natural result of both being true simultaneously. No policy required. No enforcement required. Just physics and probability operating over time. That explanation is the one that all the engineering in this briefing points toward, and it carries the most direct implication for what Earth is and what we represent. The barriers to alien visits to Earth are, in almost every case, the same barriers to human interstellar missions. Fuel math, radiation, biological limits, navigation precision, deceleration engineering, the interstellar medium, the time dilation problem, the communication lag. These apply symmetrically to any civilization trying to cross light years in either direction. What this symmetry reveals is that the question was never simply about them. It was always also about us. Humanity is currently at a specific and measurable point in the arc of technological development. We have the basic science to understand what interstellar travel requires. We have the engineering to begin early steps toward it. We have the industrial base, the computational power, and the scientific literacy to read the problem clearly. We also live on a planet whose atmosphere, water supply, and biological systems are changing faster than at any point in recorded human history. driven directly by the energy technologies that are simultaneously our path toward greater capability. The filter, the threshold between a civilization that destroys itself and one that survives into interstellar capability, sits somewhere in the territory we are currently crossing. This is confirmed by the logic of the Fermi silence. If every civilization faces these barriers and the galaxy is quiet, then either the barriers are insurmountable or the civilizations that might overcome them collapse before they do. The path to becoming the kind of civilization that could send missions to other stars or detect and interact with missions arriving from them runs directly through solving the problems of our own planet first. Energy systems that do not destabilize the biosphere. Resource management that sustains industrial capability without exhausting the foundation it rests on. Social structures resilient enough to maintain purpose and cooperation across timescales longer than any current institution has survived. These are engineering problems in the broadest sense, not solved by rockets, but by systems thinking on a planetary scale. The physics of interstellar travel will not change. The distances will remain the same. The fuel equations will not relax. But a civilization that survives its technological adolescence intact, that passes through the filter window without collapsing, has the time on the other side to develop the solutions that the equations demand. Nuclear pulse drives, antimatter production at scale, non-biological interstellar travelers, and possibly physics we have not yet discovered. Every generation of engineers who works on these problems, and every generation of citizens who builds the social and political structures that keep civilization stable enough to fund that work, is laying the groundwork for the only interstellar civilization we know for certain exists. This one. The universe may be full of civilizations that got this far and stopped here, or went quiet here, or found the filter too high to clear. We are still inside the window. That is not a comfortable fact. It is a useful one. Stand at the end of this mission briefing and look back at everything the math has said. The nearest star is 25 trillion miles away, and our fastest spacecraft takes 70,000 years to reach it. The speed of light is a hard ceiling confirmed by every experiment in the history of physics. The rocket equation demands fuel loads that no solar system could supply for a crewed mission with conventional propulsion. Antimatter offers the physics but not the production timeline. Nuclear pulse drives were real proposals that reached scale models before law and politics ended them. Laser sails could push a chip to the stars in 20 years, but cannot stop it at the destination, and cannot carry a living cell. Radiation would kill a crew before they arrived. Dust, at relativistic speed, hits like explosives. Time dilation disconnects travelers from their civilization. Deceleration costs as much as acceleration. The generation ship requires social engineering across 15 generations, with no solution in our history. Suspended animation for decades is medically unsolved. Navigation across moving stars requires predicting positions centuries in advance. Communication lags make real-time coordination impossible beyond a few light years. These barriers do not describe an impossible universe. They describe a universe that defaults to isolation and requires extraordinary effort to overcome. Every civilization in the galaxy faces the same list, the same fuel equations, the same radiation environment, the same light speed ceiling, the same biological fragility of carbon-based life, the same information lag that makes distant targets look like old photographs before you even launch. If any of them have overcome these barriers and reached Earth, they have done so at a cost and through methods so far beyond our current understanding that we should approach what that means with genuine humility. We would be, relative to them, roughly where a Neanderthal community stands relative to a modern aerospace engineer. The categories we use to think about technology, fuel, navigation, speed, would overlap with their capabilities the way a flint hand axe overlaps with a spacecraft. And yet the silence persists. The Fermi paradox remains unresolved. Our sky, scanned for decades, returns no confirmed signal. Our solar system, surveyed for centuries, contains no confirmed artifact. The galaxy, observed at every wavelength we can access, shows no megastructures, no Dyson spheres, no signatures of industrial activity at scale beyond individual stars. The most grounded interpretation of this silence is not that we are alone. The universe is too large and too old for certainty on that question, in either direction. The most grounded interpretation is that interstellar contact is genuinely hard for everyone, and that the barriers described in this briefing are not human failures of engineering, but features of the universe that apply to all intelligence everywhere. We are not behind schedule. We are not missing something obvious. We are a young species on a single planet, having existed for an eye blink of cosmic time, looking out at distances that reduce even the fastest things in the universe to centuries of travel. The most honest statement this mission briefing can end on is this: the question of whether aliens can visit Earth is ultimately a question about what the universe permits. And the universe, as best we can measure it, permits it only at costs so high that any civilization paying them has earned the right to call itself extraordinary. We have not paid those costs yet. We are still calculating whether we can afford them, and the universe, silent and vast and indifferent to our timeline, is not waiting for us to decide. The only decision that will ever change the answer is the one we make here, on this planet, about whether we intend to still be around and still be building when the physics finally gives us an opening.